So, hello everyone, this is Jiayu Xu here. So today I'm going to deliver presentation about my topic for the class Advanced Computer Vision. And my topic is the survey on coordinate transformation and its application in computer vision. So let's start now. So first about the abstracts. And now firstly, this paper includes affine transformation and rectangular coordinate transformation. So briefly, summarize the affine transformation and rectangular coordinate transformation, and give some classical examples. And let's start. So the outline of my presentation will be first talking about the affine transformation, and then we are going to talk about the rectangular coordinate transformation. And thirdly, we're going to talk about its application. And totally, we're going to discuss about three different applications about the uh, coordinate system transformation today, and we'll see that later. So now first is about the affine transformation here. And so first, what is it? What is it? What is affine transformation? So to talk about this problem, I want to, well, discuss this problem in the 2D way because 2D is really clear and simple to see since we can only use an image to see everything here. So now firstly, imagine we are having the sine lift as the original image, which is the biggest one here. And together with is our coordinate system indicated by the sine color here. And so with the affine transformation, we can map this image to other coordinate systems. And for example, the red one, the blue one here. And as we can see here, the two coordinate system, the affine transform coordinate system of the red one and blue one here doesn't necessarily have the same angle as the sine coordinate system have. So we can do like different things like scaling and changing the shape of the images and a lot of things. So how do we do it? So firstly, we have the original affine coordinate system called LOTA here. And we want to map a point here to in the LOTA to a new coordinate system pi here. And so now we should firstly understand where the new coordinate system pi is, and in the way we want to represent it in our LOTA coordinate system, the original coordinate system. And we should know exactly how this pi coordinate system looks like in the way we want to represent it in the LOTA coordinate system. And so now the original is at the x0, y0, and the two base vector of pi is a11, a21, a12, a22 here. And so now we want to represent, so now with this equation here, we can represent any points in LOTA coordinate system in the way only using the parameters that are in about the pi coordinate system. As we can see here, the a11 and x new here, a12, y new here, x0. These are all the parameters about the new coordinate system pi. So now we can find the relationship between the two coordinate systems. And the point xy here is the coordinates in the LOTA coordinate system. And the new xy here is coordinates in the pi coordinate system here. And a everything here is known except this new two xy and two equation, two unknowns. This is really simple math problem. And for 3D, this is something like we just add a new dimension here. And this is pretty much the same. By observing this equation, we can also have like the similar thing here. So everything here is also known, and a1, a21, a31 is also something we know here. This is also the way we want to represent the base vector about pi, and they have three base vector, of course. So we have three equations here, and three equation, three unknowns. This is also like another simple math problem, just a little bit harder than the 2D one. So now we can represent any points in LOTA coordinate system in the way of pi coordinate system. And if we want to like get represent image is basically like many points and many vectors, and vector is basically like 2 points. So 2 points create a vector, and a lot of vectors and points create images. So we're basically doing this a lot of time before if we want to change the image. And we can also write this in a really simple way. So this looks clearer and easier to understand. The A matrix here is where we're gonna do the shaping, scaling, and everything, and the B vector here is about the simple translation, simple moving here. And by different the matrix which represent showing this picture here showing is the A matrix here. So by setting it to some like special cases, we can do translate, scaling, rotating, shearing, and reflecting, and many other things. Literally everything. So for this part, we're talking about rectangular coordinate transformation. So actually, rectangular coordinate transformation is like a special case of the Avent transformation we have talked about before, because in the Avent transformation, we didn't expect the coordinate system to be rectangular. It could be any angles. But here we want it to be rectangular. So for the matrix A here, we should have some restriction, because we know that the two coordinate system has to be two rectangular one. So now the matrix A has to be a orthogonal matrix. Well, to be more detailed, I will show in my report. If you're interested in that, you can see my report. And so now we're going to talk about these applications. Firstly, it's about the phase alignment. So also we're gonna talk about what is phase alignment. So phase alignment is a technology, one of the most important thing in the field of computer vision. And by accurately align the detected phase images to standard position and postures. It helps to improve the accuracy of subsequent tasks such as face recognition and expression analysis and facial feature extraction, and also face identification is also important part, because we don't want those variation about the background images to infected accuracy about our detection or identification or something. So this is basically what it is. As you can see, the original picture, the face is located in different part of the images. They have different scale, different size, and different position. So we want all of them to be at the center of the picture and capture the whole images, so we can like focusing on only face. And how we're going to do this, the general step is to first locate the face. And the second step is the Avent transformation. And so we're going to start with how to locate the face first. And the algorithm to locate the face are actually really billions ways to do it. So we're only going to talk about three kind of traditional model here. And of course, there are a lot of models like BLN and SCM, I think, and also a lot of like neural network things, but they're kind of way too complicated. And of course, they can do more comprehensive and more complicated work, but they're way too difficult, like too complex for this topic. And so for these traditional ways, they are really simple, elegant, and that's why I'm choosing these three parts. And they're pretty in March, like they're well enough for our topic. So first is about the adapted contour model. So the contour model is basically focuses on the edge detection by involving the curves to boundaries of objects using energy minimization techniques. So imagine we have a picture here, and the object we want is located here, and we have a curve on it. So we are basically comparing the energy between the two sides. Well, for example, like if the energy contains is closer to our edges, it has a higher energy, and if it's outside of it, has things that is not included in our objects, it has lower energies, for example. Yeah. And for the ASM, the as is shape, is adaptive shape model. And it's building on the concept of ASM, but they're like different two ways. So it used statistical method to fit shapes within new images and make it particularly suited for text like image alignment, adjusting predefined landmark points. And as we can see the picture here, and if you're careful enough, like every point, if you can see that every point here, every landmark here has a order. So we can treat this task as a one-stroke game. So the model will remember how to draw this face starting from the 0 point. We're basically like starting from 0 point and going to drawing one line to the one and drawing another line to two. And then after going through all this point order, we can draw a face. And this is how the AIs look like. So this model is not going only remembering the shape of, no, sorry, the contour of the face, but also the inner part of our face, which is shape. And the AAM has take the appearance into account, and it's built exactly built on the ASM model. And so this allows for more comprehensive feeding for both shape and appearance of objects to new images, and offering detailed representation for tasks like facial recognition and more complex face alignment challenges. For example, for the first part, detecting the faces and detecting where our eyes is, where our nose is, and how it looks like is everything ESM can do. And for AAM, this can not only detect where our face is, but also like how our face looks like. For example, like my face looks oil today, or the other day my face looks kind of dry today and more clear today, and appearance can help us understand this. So today we're going to talk about the ASM for more detail to help us understand the phase alignment thing here. And because ASM is already good enough for our phase alignment, if we are talking about like the clear, uh, simple task. So imagine this is the ith phase, the ith image we have here, and we can represent this phase by the vector xi here so each xi0, y0 is the coordinates of this point here in our images. So since we have talked about that, every point has an order. So if we want to find a feature alignment, the only thing we need to find is to check where the eye is and what is the center, what is the uh, feature point on the eyeball, what is the number of the feature points on our eyeball. So in this example, it's 31 and 36, 31 and 36. And so for every images in our data sets, the 31 and 36 will be the eyeballs of the face, no matter what it is. So now finding three feature points for face alignment, most likely we'll find eyeballs and the center of the mouth. And in this example, it should be 3166, and center of the mouth should be 66, 64. I think it's not that clear, but it should be 64. And after we use the ASM to find where the face is in our original images. And then we have 3 points we want them to be. So for example, we want our eyes to be like on the corner of the images. We should know exactly what that point is. And now we create, well, with this 3 points, 3 pair of points, we can create 6 equation here. And the 6 equation here will help us solve all the 6 unknowns in matrix A and vector B here. So now we can understand everything here. We can have the transformation function here. We know the A is and we know the B is, and now we can, well, do the same thing to every phase here. Yeah, to every single phase here by using this function. And for the second application is about SLAM. What is it? So simultaneous localization and mapping. Well, it is a method used for autonomous vehicles, well, most likely autonomous vehicles, but also actually other autonomous things, and let us to build a map and localize your vehicle or our other robotic things in that map at the same time. So we have a sensor data. Well, since we're talking about computer vision, our sensor data should be the data of our images, and with the images, we want to like graph a map information or draw a 3D model map here. So the common task here is to, based on the video from camera, as we can see, this is the video of a camera, and we want to build a 3D or 2D map. Building a 2D map is kind of simple. Building a 3D map is actually like building a model here, and this is the picture showing here is building a 3D map. And the problem is the camera is a moving coordinate system, and our map is a fixed coordinate system, or in other words, global coordinate system. So how do we transform the camera coordinate system to the global coordinate system? And this is the rectangular coordinate system transformation gonna do. So these two coordinate systems are both three-dimensional coordinate system. So the transformation between these two is rigid transformation. And that is, in other words, we don't want the shape to change between during the change of the two coordinate system, because we want to understand the environment. We want to build a map. So we don't want the map to look weird because the change of the shape. We only change the position and its orientation. So now we can simply use this equation to represent everything. The G is the global here, and the PL here is about the parameters about our camera, and RT here is the parameter about like the rotation and translation here. So for P here, the P matrix here is represent a perspective of projections which transfer 3D coordinates into 2D coordinates as seen a center viewpoint. This is our camera view because camera is viewing a 3D world. We want to map it to images. It's 3D to 2D. And matrix typically include focal length f here. And actually, if we can also change the parameter 1 here, 0 here to some other parameters. If we want to do some scaling and other thing, we can change this. We of course we can do this, but well, since we're building a map, so in this case, we probably don't want to change up everything. So one is already pretty good here. And the focal length here cannot be well calculated by a computer vision. We should know f in advance just seeing our camera. This is the parameters of our camera. And also the L here is also the matrix usually represent a translation within the camera cover system before any rotation have taken place. And it might corresponding to the adjustments within camera's length and focal plane. So this is also something that is related to our camera itself. And third part is about the R and the T. And the RT is actually something that is external or outside the camera. So R is is the rotation of our camera coordinate system, and T is the translation of our coordinate system. And during the process of our SLAM model, we're building the map. We actually, sorry, let's go back a little bit. So we actually don't know how this R and T looks like, and how do we gonna calculate the RT function. So basically in the most simple way, we have a GPS that directly shows where our robot is and what this direction looks like. But this is kind of a simple way. In this way, we can calculate the R matrix and T matrix. And in other way, we can like have a sensor that detect the movement of our the wheels or tire of our robotics. So first we can calculate how it's gonna move and how fast it's gonna spin, and based on this two information, we can build a model about its movement. And with these movements, if we know where the center point, like where our robot gonna start in our world coordinate system, we should know what is root looks like and what its direction is just using this equation. And also I have detailed information about this in my report. And third, we're going to talk about robots for brain surgery. And robot surgery, as we can see here, the core task about this problem is to let the robotic arm know the specific position of our patient has it so that it can perform surgery accurately. While for brain surgery so brain surgery is kind of a simple task for robotics because our people's heads are basically the same, so we can easily build model. But for body, we have different shapes, different things. So building a model of our body is kind of difficult. Building brain is kind of a lot easier way, even though brain is kind of looks more important to our body, but the task for AI is kind of different. So firstly, we need to obtain in advance the conversion relationships between the patient's affine coordinate system and third-dimensional model coordinate system, and the patient coordinate systems, and the world coordinate system, and the world coordinate system, and the robotic coordinate system. So after these three relationship, we will understand the correspondence between the robot coordinate system and our model coordinate system, and these two will help us finally deliver the surgery. So first is about the patient affine coordinate system and the 3D model. So before performing the surgery, the surgeon will fix 4 markers on the patient's head, and these 4 markers will be detected by camera or something. And since we are like marks these 4 markers in advance, we could be like using right dots or something. It should be easily detected, and uh knowing the position of these points in the patient head space, and also we can be uniquely determined using the affine coordinate system by using the formula as we can see here. And now calculating comparing all 4 points in different coordinate system, we can have the transformation matrix here. This is the transformation for the patient and 3D models. And similarly, we can do the same thing for the patient coordinate system and the world coordinate system. Well, but for the patient coordinate system and world coordinate system, we will have something in advance because we want to know where our patient is in our world coordinate system. And this will be done by using a binocular camera. And we have talked about this in our class for the stereo method is actually one of the way to do this job. And so if we want to talk about in the more general way for any feature points in the space, and for the points in its image in the camera, we will have multiple equation here, and using this equation we can calculate where our patient head is in the world coordinate system. And after we have the position of our patients in the world coordinate system, this becomes the same problem as we have talked before, which is the patient 3D models. And now we can do the same thing here, so we can similarly have the transformation matrix here. And for the last one is the world coordinate system, the robotic coordinate system. So this is kind of really similar, also similar. So the surgeon here can install 2 markers points, and at the end of the surgical instrument of the robot and the front of it. So now we can produce I'm sorry, like the 2 points at the end of the robot and 2 points on the starter point of the robot. So now we have 4 points. So now using these 4 points, we can similarly detect where the robotic is, using to calculate the corresponding matrix act. I also use these 4 points to calculate the correspondence matrix. And now after this, we have 3 corresponding matrix, and using three corresponding matrix, the robot can find the patients by the transformation shown below. And everything here and this is the patient 3D model corresponding here. And this is everything we have calculated. And before the three we have calculated, and now the robot can find where our surgery is, where our patient is, and down surgery. So now the conclusion. So coordinate transformation is an important part of the higher algebra and has important practical applications in many fields. And this paper simply gives an example of the coordinate transformation in higher algebra and its three applications in computer visions. And in fact, the applications of coordinate transformation in other fields are too numerous to enumerate. And computer vision has developed at astonishing speed in recent days and grow and gradually into our daily life. I believe that in near future, the computer vision will become more and more major and perfect. So coordinates transformation as one of the mathematical foundation for the computer vision technology will also play a more significant role here. And thank you for listening. That is all I want to share for today. Thank you so much.